All right. Well, how about the last new material tonight, huh? Then next time we'll review for the final exam. Might have just a little bit of new material next time if I don't get through everything tonight, in which case it won't be on the final exam, but I might, in that case, give you a short extra credit that we do in class and I'll tell you the answer to. So it'll be really easy. It's just so you've seen it before and tried it once. I don't know. We'll see how far we get tonight. See, you should ask more questions. Maybe you'll slow me down. So tonight we want to do some things with vector value functions and the calculus thereof as the main topic. And I should note that the practice problems for the final exam, I put them out this weekend. So you should have them available now. You can download them and start looking at them. Next time we'll do primarily review. So bring questions based on the practice set of problems. That's the main study sheet for the final. I might ask some other things also, but primarily it'll be off the study sheet. So vector value functions continued. Calculus thereof. I'm going to do a rather short job with some of this because the derivation is not so important right now as having seen it and used it a little bit. So I won't do quite as many proofs, but I still want to do a little bit of them in here. We'll say this, we recall that in the plane, if we have a function r of t with a vector over it, which is a vector of two components, each of which is a function. Just each value of t gives a xy coordinate, and this bracket means vector. So this gives a vector at each value of t. Excuse me, for each value of t gives a vector, and the idea is usually you put this at the origin, and then you let t run over some values, maybe from a to b. And we said that's a vector value function. The idea is you can sweep out a curve. Where here's r of a, the r vector points, right? This is a vector value function. If this is a vector value function at the origin, which is usually what we do, that's convenient because the terminal point of the vector value function is actually the coordinates of the point. In other words, r of a going to x of a, y of a, giving x of a, y of a, the vector goes to the point also x of a, y of a. That's where the curve starts. And then as you sweep through here, for arbitrary values of t, you get r of t, which is x of t, y of t. Goes to the point x of t, y of t. And then at the very end, you get the point x of b, y of b. This is what we call a vector valued function. You put in a number t and you get out a vector r. They use this quite a lot in physics, for instance. We want to do calculus with that, right? We did some curves with it last time. So what shall we say? Here's the definition just to give it. We want to do limits with this, right? So let's say that if the limit as t approaches t0 of the length of r of t, the vector valued function, minus a fixed vector L is equal to 0. So the difference between r and L gets smaller and smaller going to 0. Then we say that the limit as t approaches t0 of the vector value function is the vector L. Well, that should look a whole lot like what you did in calculus 1 with just numbers. Numbers are really, if you like, one component vectors. And so this is the extension of what you did in the limit in calculus 1, where it's f of x minus L, limit equals 0, means the limit of f of x is L, to vectors with multiple components. And then skipping over a little bit of the stuff I might do if we had a little more time, we'll say the following theorem results, which is really nice. Says, because of this, the limit as t approaches t0 of r of t is equal to L, where L is some vector with components, let's say L1, L2, by two numbers. This is equal to L if and only if because of this definition, the limit as t goes to t0 of first component of R, or we're doing this prescription here for it, is L1, and the limit as t goes to t0 of the second component is L2. Maybe I should write that again. Let's just do that and say where R of t, vector value function with ordinary function as components, x of t and y of t given the x, y coordinates of the terminal. What does that say? The limit of a vector value function is L, vector with components L1 and L2, if and only if the limits of the two components are L1 and L2 in the calculus 1 sense, right? This is limit of a function just out of calculus 1. So that's the nice thing about this definition that leads to this result, that the limit of a vector value function exists if and only if the limit of all the components exists, in which case the limit is the vector of the limits of the components. Now, having said that, we could do some simple example. I didn't even ask this on the homework, but suppose I took the limit t goes to 1 of the vector value function where x is equal to t squared and y is equal to 3t. What's the limit of that? All you have to do is this. This limit exists if and only if the limit of each component exists. So I just take the limit t goes to 1 of t squared for the first component. Limit as t goes to 1 of 3t for the second component. Well, I know this because these are calculus 1 problems. Limit of t squared is 1. Limit of 3t is 3. T approaches 1. So there's the limit. It's as easy as that. Just take the limit of each component. Very straightforward. But don't make that hard. Now, another definition. What about the derivative, right? Just like in calculus 1, once we did limits, we could use them to define the derivative. We'll define this in exactly the same form. We'll say that the derivative of a vector value function, R of t, following, what would be the most natural thing in the world to call the derivative? Well, we could say it's the limit as t goes, as h goes to 0, of f of t plus, not f, we're going to change that, r of t plus h minus r of t all over h. That's exactly your calculus 1 definition. Remember? All I did was replace f, the ordinary function, with r, a vector value function. So what this says is you just want to take the derivative of a vector value function, you just take the derivative of each component, right? Because after all, the limit here is the limit of each component. So it's very straightforward. Here's an example. What is the derivative of the vector t squared 3t? So time on it. What's the derivative of that vector value function? Easy as can be. You take the derivative of t squared to get the first component. You take the derivative of 3t to get the second component. What could be easier than that? Just do calculus 1 twice instead of once, right? We already have 2 components. So it's 2t, 3, nothing harder than that. At each value of t, that's the However, this has a very important interpretation. R prime of t, this is really a definition, but I'll just write it out. R prime of t is called tangent vector. To the curve C given parametrically by R of t over some value of the parameter t. That defines tangent vector. Why would we define it that way? Here's the motivation for calling it that. It comes from the idea of the tangent line. From calculus 1. Reason or motivation. Suppose I take some curve, C, by R of t, and again, we'll let R of t be a vector valued function with the initial point at the origin. So here's R of t at some value of t. T is kind of nice because in the sciences you can think of t as time, and this is a position along a curve. Maybe it's a brick flying through the air or something. So this is its position vector, they'll call it in physics. And it points maybe to the center of the mass of the object, which is kind of neat because if you throw like a bowling pin through the air, each point on there kind of wobbles around, except the point right at the center of mass, ignoring air friction, executes a parabola, a nice smooth parabola, and while the other stuff rotates around it. And so this is the way they usually do these problems in physics, is they'll give a position vector to the center of mass, and then they'll have an easy curve for how it moves, ignoring air friction in gravity, or in lots of other circumstances too. But if this is some object up here, and I just pick some point on the object, I call it a point object. I keep track of this one point, such as the center of mass. Sometimes in aerospace, they keep track of the aerodynamic center instead of the center of mass, because there's, when the aerodynamics come in, then this changes. But there's always some point on here in physical problems that you consider the position of the object. And so we call this a position vector. And here's why we call it a tangent vector. Suppose I take a little later time, thinking of t as time. T is called the parameter of the curve, but in general, we're thinking of it as time for physical problems. Here's another point on the curve out at R of t plus h, right? And what's this definition of derivative tell me? I'm going to take the difference of those two vectors. Here is the vector R of t plus h minus R of t, right? For the triangle picture, when we had vectors, when you had two vectors, their difference went from the first one, went from the second one to the end of the first one. So R of t plus h minus R of t goes from R of t to R of t plus h. So that's the subtraction picture from vectors we did before. And now we realize if we let h get smaller and smaller, we get the following thing. I might consider a second vector here, which is this divided by h. Maybe it's this vector. So this one might be R of t plus h minus R of t all divided by h. We know that points in the same direction because we multiplied it by the number 1 over h, right? It's the same direction, just scaled by the factor 1 over h. When h is large, this vector will be shorter because 1 over h is less than 1. But now, as h gets smaller and smaller going to 0 in this limit, which is just the calculus 1 definitional limit, but we put vectors in instead of ordinary functions, vector value functions. This starts to happen just like in calculus 1. Now, we take h a little smaller, and we go to this point, and now this is this one. This one is R of t plus h minus R of t. It goes between the two endpoints of these two vectors. And it's closer to tangent to the curve, just intuitively. But when you divide it by h, as h gets small, 1 over h gets bigger and bigger, and this might be now a longer vector. So here's r, again, the red one is r of t plus h minus r of t, just with a smaller h. And the blue one, the whole thing divided by h. And as h gets smaller and smaller going to 0, r of t plus h minus r of t gets to be real tiny vectors, but they start to look, picture at least, like they're closer and closer to tangent to the curve. And provided it's a nice curve, you can show that you actually do get a limit. And if this limit exists, then this, in general, r of t plus h minus r of t isn't getting smaller, minus r of t over h isn't getting smaller and smaller. It might approach some limiting vector, right? That's not the zero vector. And so if it doesn't approach the zero vector, what you get is a vector that's in the direction closer and closer to tangent. And the limit, we call it the tangent vector. And presumably it has some non-zero length. It can have zero length, depending what you put in there. But generally, it's not zero, so we call it the not zero length, and we just call it the tangent vector because in the limit, it fits our concept of tangent. All right, so that'll be called the tangent vector. And we can then do something like this. Find parametric equations for tangent line to the parametric curve given by r of t equals t 2t squared. Let t run from minus infinity to infinity, say. Be the value of the parameter t. At the point t equals 1. How can I find a tangent line parametrically? This is a good problem. But that's exactly what you want to do. And you might say, well, geez, this is just what I already did in calculus 1, made it harder because now we have to do parametric curves, right? Why can't I just draw the curve, find out y as a function of x, and take the derivative and do it selecting calculus 1? And the answer is you can. But now try doing that in 3 space. This is a plane curve, and so you could do it in calculus 1. Curve wandering around in 3 space, right? How do you define the slope of the tangent line of the function? You don't. What you instead do is you take the tangent vector, then you take the line that contains this point in the direction of the tangent vector, and hopefully it looks like that, and you call that the tangent line. So even though this is a simplistic problem that you could have done with calculus 1, the idea is if you extend this to higher dimensions, 3 dimensions, and you notice you do this in higher dimensions, 4, 5, any finite number of dimensions, you can find a tangent line to a parametric curve given by r of t and however many dimensions there are. And this is a really useful thing, right? If this is your rocket spiraling down, you ever see the Spaceship One descent with its feathered approach? It goes on a little helix, a spiral like this, and this could be its tangent to the spiral that's coming down or something. You want to know, that's a useful thing. If it loses thrust right here, what direction does it go? It goes in the direction of its velocity vector like that, the tangent to the curve. And I should point out, we'll say it in a minute again, but if r of t is actually the position as a function of time, it's like calculus 1. Not only is r prime of t called the tangent vector, but it's also called the velocity vector. So maybe we should write that down now. Let's just go ahead and write that. And if r of t equals position vector of the center of mass or something at time t, it is also called the velocity vector. So it's the tangent vector always, and it's the velocity vector. that is v of t, velocity vector, is defined to be r prime of t when r of t is position. All right, let's get back to our example here. What is this doing here? What kind of curve is that? Here's a thing you can do in these real simple cases where you can solve for solve in one of these for t as a function of the variable, right? So if this is x of t is t, and this is y of t, sweeping out the position at any time t, then I know exactly how to solve for x of t. X is equal to t, right? So from this one, I get x equals t, means t equals x, and I can just plug that into the other equation, and I get y. Y as a function of t is 2t squared, put in t equals x is 2x squared. So this is just the parabola y equals 2x squared that I'm sweeping out with this, right? Because y is x squared. So easy things like parabolas, we usually just let x equal t and then y equals whatever function, the function of t that x used to be. Here it is. Vector value curve, or the curve swept out by the vector value function, t 2t squared, is in fact the parabola of y equals 2x squared. And so it goes, for instance, through this point, 1, 2, right? Put in x equals 1, you get y equals 2. Put in t equals 1, you get x equals 1, y equals 2. Here it's the same thing. Now, what's the tangent line to that? We could do it in calculus 1 by taking the derivative, right? And using the point slope formula, right? We find the slope from the derivative. Calculus 1. And so we can write the equation, the tangent line is y minus y0 equals m times x minus x0, right? That's the point slope formula from algebra. And then for n, you put in what the derivative is at that point, right? You say y minus y0 equals y dx, the derivative at x equals 1. Well, let's put x0. The derivative at x0 is x minus x0. So that's what you do in calculus 1 to find the tangent line at a point x0, y0 to a curve. What do we do now? It's nicely analogous. Now what we're going to say, the tangent vector is just the derivative vector. We take r prime of t, derivative component by component, 1 for t. Derivative of t is 1, derivative of 2t squared is 4t. And then at t equals 1 it is, and we use this notation, r prime of 1 means take the derivative and then plug in t equals 1. We get 1, 4. Right? So there's the tangent vector. I can draw it up here in red or something. So it's pretty high up here. But that will be the r prime of 1 is the vector with components 1, 4. It's over 1 and up 4. And you see it looks tangent to the curve, right? But in any case, that's how we define it, right? Now, how do we get parametric equations for the line instead of doing this point slope equation for the line? What we do is simply this. We recall the parametric equations for a line. Line through a point x0, y0 in the direction v. Notice the similarity. V is now velocity, but v was the direction before. It's the same concept. It's tangent to the curve. V is equal to AB. Had this before. If you go through a point with this direction, what's the line It does that? Oh, it's x equals x0 plus at, y equals y0 plus bt. That's how we did it before. Those are the parametric equations. You could also do it vectors and say the vector form of that is r equals x0 y0 plus t. That was equivalent to these on this side. Suppose I want to write parametric equations, so I use this form. And so now t is the parameter for the line instead of the parameter for the parabola. T hat, if you want just to make a distinction. What do we have? Well, we know that it goes through this point 1, 2, because what we have r of 1, we just put 1 into r and get 1, 2, right? Put in t for 1, 1, 2. That's the point of tangent. Remember, the endpoint of r sweeps out the curve at t equals 1. This is where it points. And so the r of 1 is the position vector corresponding to r0 here. We sometimes call that r0. And then the direction vector is, in fact, a velocity vector, which again is denoted. And if we call its components A, B, then this must be A and B in the parametric line description. And so we have x equals x0, which is, well, this is x0 and y0. That's the point of tangency. 1. And this is the direction, 1, 4. And so it's plus 1t plus 4t. There's parametric equations. X equals 1 plus t. Y equals 2 plus 4t. Sweeps out the tangent line just by finding the point to the point of tangency by plugging the number into the vector value function, finding the direction by plugging the value of t into the derivative to get the direction, and then writing these equations down that we've already wrote for lines. You had a point and a direction vector AB. You can immediately write these equations for line of width direction. Now we apply it to specifically to finding a tangent line. Questions on that is a little tricky. I hope it looks like what you've done before. Here's the point by plugging in 1. Here's the direction by plugging 1 into the derivative, and we just use the point direction. The same old way to find the parametric equations for the tangent. Okay, so fun with tangents, huh? Well, I hope this looks like a natural extension of what you saw in Calculus 1, right? We have this additional note in a section I'm not going to cover, so I just want to mention it now. In Calculus 1, if position is, we call it S of t along the line. Right, so you've got a line anytime t, so this is S, you're at position S of t. What was the velocity? Velocity was S prime of t. But what was the speed? It was the absolute value of S prime of t, right? So if you're going backwards if your velocity is minus 2, you're saying you're going backwards at 2 miles per hour, your speed is still 2 miles per hour. Going back and forth along the line. Now what we can do is this in more dimensions. Now, if position in the plane or in 3 space, all this carries over to 3 space and 4 space and so forth, just obvious as can be. Position is a vector to a point in the plane or to a point in 3 space, then You're in a plane instead, and you're moving along a curve, C, given parametrically by this vector value function R whose endpoint sweeps out the curve. And the velocity is now a velocity vector. It's R prime of t. So instead of talking about the velocity, you talk about the velocity vector, which is now tangent here. And what shall we call the speed? The speed will be the length of this, just like if you had S prime was a certain number, you thought of that as your velocity in this direction, and its absolute value was the length of the velocity vector, right? Absolute value is length in one dimension. Similarly, speed is the length of this vector, length of R prime of t. So this is a useful thing, physics and that sort of thing. Every object moving along a curve like this with position vector R of t, you can take the derivatives to find the velocity. You can take the length of the derivatives to calculate the speed, and so it has a speed, which is the length, and a direction that it's moving. Calculate with the R tangent. So that's kind of a side comment. I don't think I'll do a problem on that because it's not homework, but you should do. Speed is the length of the velocity vector. All right. Wish we had one more lecture, but I'm really glad we don't have one last. Because this is kind of important material, I think. All right. But I don't want to do anything new next time, really. Interestingly, the rules of calculus 1 carry over completely naturally. Right? Suppose, for instance, I take the derivative of a constant vector. What do you think I get? I have that rule for the derivative, which makes it as the limit of R of t plus h minus R of t all over h. Find out the derivative of a constant vector is zero. Is a zero vector. If you take the derivative of a constant times a vector value function, you just pull the constant out. C times derivative of R of t, etc. Right, let's do one more. Suppose I have R1 of t, one vector value function, R2 of t, another vector value function, and I take the derivative. The derivative of the sum is the sum of the derivatives, provided they both exist. Now we'll say etc. You can put a minus on here because it carries over to the minus too. So etc. In particular, what about a product? Oh boy. Well, in fact, both the dot product and the cross product satisfy the product rule, etc., including this one, which we won't prove. It's not worth the time. But I have a vector value function R1 of t dotted another vector value function R. And then take the derivative. What would you guess it would be from the product rule of calculus 1? Derivative of this times this plus this times derivative of this, right? Except we'll use dot product instead of the product of calculus 1, because calculus 1 product only applies to derivatives of functions, not vector value product. All right, so this is R1 prime dot R2 plus R1 of t dot R2 prime. Let's see, how about that? Derivative of the first times the second plus first times derivative of the second. You can add in either order. It doesn't matter which one you put. Vector addition goes in. It's out of the way before it clutters. So very cool. All your derivative rules are absolutely natural. And then if you really think about it, suppose these vectors have one component. They're one component vectors. Then what happens? just the ordinary product rule. It becomes R1 times R2, derivative becomes R1 prime times R2 plus R1 times R2 prime. So in one dimension, this is the product. This generalizes the product rule in any number of dimensions. This applies for two components like we've been doing today, just to be fast, but also applies to vectors in 3 space, right? Where all these apply in any dimensions. 1, 2, 3, ad infinitum, right? For instance, in 3 space, you have a vector that's out to some point here at the corner of the box. And you can have a curve swirling around in 3 space, and here's R of t. Now it has 3 components, x of t, y of t, z of t. And the product rule, the dot product still applies. So these apply in any number of dimensions, 1, 2, 3. And the proof is completely analogous. What you can do is for general n dimensions, and then all that follows. All right. Now, furthermore, in 3 dimensions, because the cross product is only defined in 3 dimensions, you take R1, a vector valued function, cross a vector valued function R2. What do you think you get if you take its derivative? It's a product rule again. One of the reasons these are both called products is that they follow the product rule for derivatives. Sometimes also called a derivation. R1 prime of t cross R2 of t plus R1 of t plus R2 prime of t. There it is. The product rule also applies to the cross product. Pretty neat. So it's real easy to keep track of this stuff. The material here is not too hard, but there is a lot of it. So anything that says a lot of it's hard, right? When I took Spanish, all the words were easy a couple at a time, but when they give me 20, my head would swim, and then I couldn't remember 2 anymore. Same thing happens with classes when they get too big, unfortunately. All right, so if you have 5 students, you learn their names. If you have 20 students, maybe you learn 2 names. You gotta work on it, otherwise that happens. So I don't want to do that. All right. I'm so sorry I don't get to meet you all this semester more. I just feel awful if we don't get a more personal class where you can ask questions and so forth. Next semester will be better. And we're all going to regular classes, and provided we don't get a new strain of COVID coming around, everything should be good again, I hope. So it's very fascinating. There's a nice calculus model for disease. And the simple model shows that if you get past that herd immunity in a community, then the disease will die out exponentially, which is fast. Exponential decay is fast. But if you're below herd immunity, it will grow exponentially, which is terrible. That R factor, which is hard to say what it is because we started all the R number. We started all social distancing before we found out what the real number R number is. Everybody got so scared of it in Italy in the early stages that we don't know if it's in an unconstrained society how fast it would spread. But suppose it's about 3 or 4 from what I can tell. That means each person on average passes it on to 4. Maybe if they do that within a week or when they catch it, then what happens is after 1 week, if you start with 100 people, say, after 1 week, you'll have 400 people. After 2 weeks, you'll have 4 times that, 1,600 people. After 3 weeks, you'll have 6,400 people. And if after 10 weeks, you'll have, actually, let's say after 5 weeks, you'll have 1,024 times the original amount. In other words, you'll have over 100,000 people with this. And if you go another 5 weeks or 10 weeks, you'll have over 1,000 times that. You'll already have 1 million people. Go to bigger than this. It's this times 1,000. So this is greater than 1 million. That's to think about 1,024 times 1,024. And so it's greater than 1 million people already. And after 15 weeks, you'll have over 1 billion people. And so this, I mean, that's only 4 months. This thing can go from 100 people to 1 billion if it's unconstrained and, you know, nobody's immune. With an R factor of 4. The really, really bad one is measles. It has an R factor, if I think about it, 12 or something like that. I was talking to a man who grew up when measles was there was no vaccine for it. And he said the whole class would just be gone for 2 weeks when measles came around. Terrible. You know, chicken pox was a real common thing. It wasn't as devastating as measles, but you can see in a community there'd sometimes be a lot of measles, a lot of chicken pox, and sometimes not, and sometimes, you know, and it would go up and down. But on a large scale, it's amazing how these diseases work until people became immune. If you looked over the whole United Kingdom, I saw a graph, and it just went up like this and down like this in a nice oscillation. In selected pockets where they retained some herd immunity, they would not get this bump. They'd get fits and scatters, and you wouldn't know how it would go. They'd get occasional spikes. But over the whole of the United Kingdom, they started graphing this until vaccinations came along, and it all changed. If you look that up online, there's very interesting things you can do with this. But there's a calculus model for that point. And so if we can get past herd immunity, then this thing will die off exponentially until people start getting not immune and going to do something again. So that's my digression to wake you up. All right. Lots of fun knowing mathematics and models like that, but that's just a simplistic model that tells you that. There are more complicated models that take into more factors, obviously. Let's see. Here's a theorem that I have to put that before the boring theorem, and you'll fall asleep, right? If R of t, a parametric vector valued function, has constant length of R prime, the tangent vector equal to a constant C, then it turns out this interesting property holds. R of t dot R prime of t is equal to 0. In other words, the position vector is perpendicular to the tangent vector. Right? Dot product equals 0 means they're orthogonal. Means they're either non-zero and perpendicular, or at least one of them is a zero vector. Fascinating result. If you think about it intuitively, it's absolutely obvious. I like the intuition better than the proof, but we're going to do both. Intuition, what does it mean for a position vector to have constant length? Like suppose it's C units long. That means if it's put at the origin, it just moves around and around with the endpoint C units from the origin. So it moves around on a circle of radius C, right? It just keeps going around like this. It might go this way and then that way, right? But what do we know about the tangent vector of this curve? Since the curve is a circle, what direction does it point? Perpendicular to the circle, right? The tangent is perpendicular to the circle. Oh, obviously. Vector moves around in a circle, and tangent vector is perpendicular. That's the intuitive way to understand it. Remember, it's easy, right? I love that one. The proof, I suppose you could do a proof using that in the detail. The easier proof is this. This is one proof I'll do tonight. If the length of R of t is a constant, then this will bring into play something else, another property I wanted to point out along the way. So there's method in my madness to teach you one more thing too here, not just teaching you the proof. Then what happens? What is the derivative of R prime of t of the length of r prime of t squared. What is the length of, what's the derivative squared? Well, the length of r prime of t is c, so this is just c squared. Prime, which is 0, right? So we know the derivative, the length, excuse me, the derivative of the length squared is 0, but here's why I also introduced this. We know that the length squared of any vector is the dot product of the vector with itself. Here's why, in case I think we didn't say this before. For any vector, it doesn't have to be a vector valued function. Any v, and it can have any number of components, just not just 2, but let's do it with 2 for simplicity. What is the length of these? What is v dot v? Well, it's v1 times v1 plus v2 times v2 by definition of the dot product, right? With itself. But that's v1 squared plus v2 squared, right? Which is the square root of v1 squared plus v2 squared. Squared. Square the square root gives you this back. Oh, but this is the length squared, right? Length. That's a useful property to know. You'll see people write this down. I want you to say, hey, where'd that come from? I didn't learn that calculus. Yes, you did. All right. So the length of r prime squared is r prime dot itself, right? By that property. But now what's this dot product? Well, by the product rule, it's I wrote this wrong. It's supposed to be r prime here. R is constant length, like I wrote up there, and then I wrote prime all the way down. Sorry about that. Take the primes off of here. Right. Sorry about that. I don't used to writing prime. So C is equal to the length of RT. This is correct. The length of RT squared is RT dot RT by that theorem. But now by the product rule, this is R prime of T dot R of T plus R of T dot R prime of T, right? By our product rule for the dot product. So now remember, the dot product goes in either order and gives you the same result. So this is 2 of the same thing. This is 2 R dot R prime, right? Well, if 2 of these is 0, then it follows that 1 of these is 0. R dot R prime is 0. Tell you what QED means yet? I think I did it now. Okay. It's lat poder demonstratum, which was to be shown. So that's what we wanted to show. That was more popular when I was young than it is today. I don't see it so much anymore. Anyway. Yeah. It wasn't too long ago, just before my time, I think, when they were still doing a lot of geometry out of Euclid's books. There's still 7 volumes. You can get them in Dover reprints. They're beautiful. It's the most famous math book of all time. And maybe I told you, the second most published book after the Bible until recent years. May still be, I don't know. And so it was, anyway, but they stopped using it. It may not be so popular anymore. You know, maybe they publish more income tax than Bibles these days. I don't know. But I mean, he's the greatest textbook writer of all time, if you will. Euclid was. And so everybody learned Euclidean geometry in the mid 20th century out of Euclid's famous works, but it was all done with a compass and a straight edge. And so it's kind of switched over to coordinates and been more abstract since then. All right, so there's another theorem that's useful. And now let's see. we define derivatives, we also want to do integrals. Similarly, an integral of a vector valued function, R of t, dt, is just done component by component. The derivative goes component by component, and it follows the antiderivative going back the other way, goes component by component too. So this becomes integral of, you have R of t having two components, x of t, y of t. Then all you have to do is integrate x of t for the first component, integrate y of t for the second component. But it follows now that you get an arbitrary constant for each component. And so the antiderivative R of t is any antiderivative plus an arbitrary constant vector, right? With an arbitrary constant for each one. For example, if I find the antiderivative, let's go back to this, t and 2t squared. What are all antiderivatives of this vector value? Well, we just integrate component by component. It's the integral of t and the integral of 2t squared. And then now you just do calculus 1. Integral of t is t squared over 2 plus a constant. And integral of 2t squared is 2t cubed over 3 plus a constant. So there's all antiderivatives. And you can also write it in this form. It's any antiderivative, t squared over 2 and 2t cubed over 3. That's right, that's one antiderivative, plus an arbitrary constant vector with components c1 and c2. So both of these forms are convenient. That's how you do an integral for vector value function, just component. All right, now I'll get to something more interesting. Arc length. Now we did derivatives, we did integrals. What else can we do? Oh, yeah, arc length. That's one. This one I'll do the derivation of. It's worth seeing also. We did something like it previously. This should look very similar, so it's hard to pick up. Suppose I give a parametric curve, again swept out by a vector valued function R of t. So curve C swept out by R of t equals x of t, y of t in components. Let's write it in the other form. You can also write it as x of ti plus y of tj. That means the same thing as x of t, y of t in this form. Right? This is just a different notation, the ij notation for the same vector, with t running from some point to some point. It might be minus infinity. But if I go over a finite interval like that from here, R of A over to this vector, R of B, suppose that R prime of t is continuous. Talked about derivative. Continuous just means that each component is continuous. So that means that x prime of t and y prime of t, the derivatives of the components, are each continuous. Find continuity with vector value function. So the nice thing here is it all goes straight over. And the curve is regular. Well, actually, I don't even need this yet. But let's leave this off for now. Then what do we want to do to consider arc length? Let's consider doing this. partition the interval for t, a to b, as follows. A is equal to t0. You go to t1, and then from t1 to t2, bigger and bigger values. That is, t0 is less than t1, is less than t2, and so forth. All the way up to tn minus 1, and tn with tn equal to b. We call that a partition of the interval from a to b, breaking it up into these closed subintervals. N of these. 1, 2, 3, n. Now, we can estimate the length of arc by taking line segments from here to here, 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 all the way down from here to here. And so what's the length of each line segment? We know that from algebra, right? The length of a line segment is the square root of, well, let's see, this is x1, y1. This is x0, y0, and so on. Suppose we take the kth segment somewhere in here, and this is xk minus 1, yk minus 1, to xk, yk, the kth segment. And we want to find the length, lk, of the kth segment. What is it? Well, it's the distance formula, right? It's square root of the difference in the x coordinates. xk minus 1 squared plus yk minus yk minus 1 squared. So that's the length of the kth line segment. But what are these points here? xk means x of tk, and yk means y of tk. And similarly over here, this means x of tk minus 1, y of tk 1. And so the line segment length is the sum, k equals 1 to n, since there's n segments, of the length of the segments. X of tk minus x of tk minus 1 squared plus y of tk minus y of tk minus 1 squared, square root, and we sum that k going from 1 to n. That's an estimated arc length. Now, if we take the limit as the number of segments goes to infinity, with the width of the widest partition, interval in the partition going to 0. So that's tacitly assumed here. When we say n goes to infinity, it's with the widest interval going to 0. So sometimes the book will write this instead. Instead of n goes to infinity, they'll write length of the partition goes to 0, which means the same thing. So you use either of these notations, it means the same thing. What happens? Well, this is also equal to, by the mean value theorem. Well, let's do some algebra first. Limits n goes to infinity of the sum k equals 1 to n of the sum x of tk minus x of tk minus 1 over delta tk squared plus y of tk minus y of tk minus 1 over delta tk squared, all times delta tk. Where I'm going to let delta tk denote the length of the kth interval, be tk minus 1. K running from 1 to n, so you got delta t1, delta t2, all the way up to delta tn. And see, this is the same one algebraically, right? Because I'm multiplying the outside by delta tk, multiplying the inside by 1 over to the square root 1 over delta tk squared, so these cancel. The delta tk's don't cancel, it's the same thing. Now I'm in a position to use the mean value theorem for derivatives. This is why we said, if you took my calculus one in class, but it won't help you to solve your applied problems so much to know the mean value theorem, but it comes up in all sorts of proofs. You need it to prove things. If you're a math major, you absolutely need this. what is this? This is the limit n goes to infinity. Sum k equals 1 to n. And now square root by the mean value theorem for derivative. What is this? This is the slope of the secant line in the tx plane. All right, the slope of secant. F of xk minus f of xk minus 1 over delta xk was the slope in calculus 1 of the secant line. This is the slope of the secant line in the tk plane. By the mean value for term for derivatives, this is equal to f prime at some intermediate point tk star. And so we square this instead because the slope of the secant line is equal to the slope of the tangent line. So what I should, not f prime, x prime. X is the function. And the second one, this is the slope of the secant line in the ty plane. And so it's equal to the derivative of y at some intermediate point, tk star. I'm going to have to call this tk double star technically because its level will be a different value squared, all times delta tk. By the mean value theorem for derivatives, MET. There is a point, as long as the derivatives are continuous, and that's what we stipulated, right? This is true. Now we've got it, because what is this? If I take away the second star, this is the definition of the integral of this function, right? We said this, when I write definite integral from a to b of f of x dx, what does this mean? This is notation for limit as n goes to infinity, sum f of xk star delta xk, right? K equals 1 to n. That's the definition of the definite integral. We apply it here. This is limited sum of a function of tk star times delta tk, so it's the integral with respect to t. By definition, this is the integral of this function evaluated at t, x prime of t squared plus y prime of t squared square root dt going from a to b, the interval of t value. There's the arc length formula. Now I did a little slide of mathematical hand here. Technically, this is a different point y double star, not the definite. They have to be the same point to make the difference. But there's a theorem that says if these are continuous, you get the same result whether or not these are the same point, as long as they're in the same interval. So I'll say that with that little mathematical sleight of hand, there's a theorem that says it's the same result. And put a footnote. Theorem applied here. I'm waving my hand at. Then you get this result. All right. So this is the arc length formula. It has a nicer form too. You can also write this as the integral a to b. Wait a minute, that's the length of r prime. I could also write it as length of r prime dt. This notation is nice because this only applies to plane curves, right, where there's two components. This one applies to any number of dimensions. It's the same formula. It means the same thing. But if you have more components, you just root sum square all of them. So either formula works in the plane. In more dimensions, you just use this one. And this one is so easy to remember, right? Just integrate the length of r prime. And it corresponds to calculus 1, where if you wanted the distance traveled along a line, how did you find the distance traveled? Displacement, you could get, you don't want to see this, I don't know, f of b minus f of a by integrating f prime of x from a to b's, right? By the fundamental theorem of calculus, that's f of b minus f of a. But what if you were going back and forth? You didn't want to know what's the displacement. This is between where you started and ended, but how far you actually traveled. Then the distance traveled was the integral from a to b of absolute value of f prime. Right? That gave you the distance traveled, because otherwise when you're going back, you're making negative distance here, but now this makes it all positive. This is similar. This is taking the integral of the length of r prime instead of the length of f prime. It's the same concept, just and sometimes it's hard to see that out of the book, really. But it's just extending that. Instead, you take the length of r prime and integrate it to get to arc length. So that's the theorem. For under those conditions that r prime is continuous, you have that the length of the arc length of a curve is the integral from A to B of the length of R prime of t. This is much more powerful than our previous arc length formula. The following sense. Remember we had an arc length formula earlier in the book? Note, if you have the special case, that y equals f of x, right? Then what happens to this formula? Well, we can make a parametric curve. We can let x equal t, and then y is f of t, right? And this is, and then a is less than or equal to x less than or equal to b. Now t goes from a to b. And by this one, I don't want to, what do I call it, star, by star, we get that the arc length is the integral from a to b of the square root of, see here, x prime of t squared plus y prime of t squared dt is the integral from a to b. Well, if x is t, then its derivative is 1, so its derivative is 1 squared plus y prime squared dt, y prime of t, if you like. That's our formula from before. Remember this arc length formula? Our old arc length formula was this, integral 1 plus square root of 1 plus y prime of t. It's just a special case of that now. We have generalized our formula, right? This one worked only for curves where y was given as a function of x, which meant no vertical line could intersect it more than once, right? Y equals f of x, x going from a to b. Now what we've done is we've said for, this is the old stuff. The new stuff is that we can have a general parametric curve, which means it doesn't have to be y a function of x. It can wander all over, giving these points x of t, y of t as you go, because each x and y are each a function of parameter t. And now you can do an arc length of a curve that's not a function. That's the idea. This formula runs that this one could only do y a function of x. That one does much more general curve. New one is L equals integral a to b, length of r prime of t dt, and it's the same old formula if y is equal to f of x. So let's try one of those. Here's a fun one. Suppose r of t, we need to do a three-dimensional problem here, is equal to this, this vector value function. 3 cosine t, 3 sine t, t. But that's sweet about it. Here's what you can do. You can look down on top of it and just look in the xy plane, right? And this is x of t, this is y of t, and this is z of t. Right? There's a vector value function in 3 dimensions. And in the xy plane, ignoring z, just looking down on the z-axis, what do I get? I got 3 cosine t, 3 sine t, it sweeps out a circle of radius 3, right? Because the 3 cosine t sine t would be the circle of the unit circle of trigonometry when you multiply each by 3, sweeps out the circle of radius 3. So there it is, the circle of radius 3. Now, what that means is that in 3 dimensions, remember when a circle comes in 3 dimensions with c unrestricted, we would get the cylinder of radius 3. So these first 2 components tell us that whatever the curve is, it moves along the cylinder of radius 3 in 3 space. And now what does t do? What does c equal t do? Well, you start here when t equals 0. 3 cosine 0 is 3. 3 sine t is 0 and t is 0. So that's a point on the curve just by plugging in t equals 0. And as t evolves, you're going on the projection here, you're going around and around counterclockwise because t is the polar angle. We're going around, but at the same time, t is climbing up the z-axis. So what you have is this spiral shape, like a spring. It's called a helix. That's what this is. When you have a multiple of cosine, a multiple of sine in either order, followed by a linear function of t, at plus b. It's a helix. What do we do? How about we find the arc length of one wind of the helix? On, like this is a spring. I wonder how much longer it is than if I forgot. Let's not make this t. I wanted this to be 4t. Make my numbers better. 3t and 4t. 3 and 4. And it can be any multiple of t plus a multiple and still a helix. Right. And so for L, find the arc length for one wind around the helix. That is 0 less than or equal to t less than or equal to 2 pi. So it goes right around the xy plane. What is it? By our formula, by star, the arc length is the integral from 0 to 2 pi of the length of r prime. Right? Just like absolute value of f prime dx in calculus 1. But what is the length of f prime in 3 dimensions? It's the root sum square of 3 components. So first we calculate r prime by taking the derivative of each component. The derivative of 3 cosine is minus 3 sine. The derivative of 3 sine is 3 cosine. And the derivative of 4t is 4. So there's what I have to take the length of. What the length of that vector is. In general, you can see arc length is terrible to compute because the square root of the sum of the squares of these, usually you can't integrate it. However, I picked a Cook problem when we actually do it for this one. I just wanted to point in general, you just get a computer to estimate this accurate because it's too hard to do the antiderivative. But if you think about it, it's minus 3 sine t squared plus minus 3 cosine t squared plus 4 squared t. That's the length of the vector 3 space. X squared plus y squared plus z squared square root, we said. But what is this? 9 sine squared plus 9 cosine squared, or 9 times sine squared plus cosine squared, but sine squared plus cosine squared is 1. This whole thing is just 9. So what we have here is the integral from 0 to 2 pi of the square root of 9 plus 16 dt. Some of those squares is actually just 9. Pythagorean identity from trigonometry, the sine squared plus cosine squared. Oh, but this is just 5. See, I wanted to pick better numbers. So this is 5 integral from 0 to 2 pi dt. This notation integral dt means integrate 1. There's a 1 assumed here. And so this is just t. 5 times t evaluated at 0 and 2 pi. Oh, it's 10 pi. There it is. You can compare with the arc length around a circle of radius 3. If I just went around the xy plane, it's 2 pi r, right? 2 pi times 3 it would be 6 pi. So if I went around the circle on the xy plane, here this would be 6 pi. But by climbing up and going around one line up here, I actually get 10 pi. So that was the increase in arc length spring over the circle. Well, fun. There's a nice end of the semester. I might mention, like I said, just a little bit of additional material at the beginning next time. Maybe we'll have an extra credit problem depending on how much there is. Any questions on this? It's just time to go. All right, bring lots of questions next time, and we'll go over this and try and get it down next week. Oh yeah, I got to put the homework in. I made the homework, yeah, otherwise I have to email. I way cut down my original homework I had because there's too many sections in here. I just want you to do these things just like we did. 12.2, number 11 and 19. I gave you 12.1 last time, didn't I? It's on vector value functions, but 11 and 19, this is on calculus of these, just taking derivatives kind of thing. 12.3, 5, 9, and 25. And then 12.4, arc length, 5 and 7. Okay. So this is like the tangent lines in one of these, and this is like arc length of these. So it's a promise we did tonight.